Hello everybody, and welcome to this presentation, this talk about site calibration with PROJ and WKT2. I'm Javier Jimenez. You already presented me, thank you. You can find more information about myself on my GitHub profile. I'm currently the technical coordinator of P4SRS team at Pix4D, photogrammetry company. And I want to thank, before starting, Juan Hernando. We made this paper together, and Alexander Nervas, that he should be here helping me, but unfortunately it was not possible. This paper, you have the link there, this QR code. The purpose of the paper was to offer an open source solution for something that's already out there, but done by private companies with proprietary solutions. Now, black box, they are not well documented what's going on. They just work. Those manufacturers are mainly hardware manufacturers, total stations. We are developing this solution in our products, mainly so far in Pix4D Catch, and we want to make it an open solution that fits perfectly with PROJ. That's the library that we are using. By the way, no AI was harmed during the making of this paper. So what we are going to see here. First was a site calibration. By the way, anybody knows here what's a site calibration or site localization? Okay. So I want to explain why that's interesting, why we need it. Some use cases, the mathematical things are going underground. Then what's WKT2 and why it's an interesting solution for that problem, and PROJ, that's an open source library, how it's helping us. So first, what is a local coordinate reference system? Those are some aliases of the same concept. It's a Cartesian non-georeference coordinate reference system with an arbitrary origin. So you have your origin at some point, probably at your construction site, and you have a Cartesian x, y, and any direction, any units, and no reference to the Earth. Okay, surveying. How was done surveying before GNSS era? It was done using mainly theodolites. That's this device on the black and white screen. There are bigger pictures later on the presentation. That's measuring mainly angles. High accurate way to measure angles on the field. Also distances, but mainly angles. Nowadays, what's used is this device, the same idea, but with a computer and a laser beam that makes things easier. That's a total station. I don't know why the name. That lets the surveyors and topographers to make triangulations on the terrain. And with this triangulation, you can deduce later the coordinate of any point in the field or in the country where. But nowadays, with these GNSS constellations, what we use is a GNSS receiver and making some maths to get the coordinate, an absolute coordinate respect to the, well, a georeference coordinate. So why do we need site calibration? So as I said before, local CRS are not georeference to any global system. They're absolutely floating. And GNSS measurements are in global coordinates, so they are georeference. And if I want to use my GNSS device on my construction site, that's a typical example of a local coordinate reference system, how do I use it? So I have my local system, and I have my GPS, and I want to use there. So site calibration is going to be how to convert my coordinates from my local CRS to a well-known CRS, and vice versa. Here are two use cases. I'm sure there are more. One is that now with this local site calibration, I can quickly measure with my GPS, with or without RTK, depends on how much accuracy I want. I can quickly measure and transform them to my local coordinate system. Using a total station is something much slower. You need usually a professional to do that. Or I can fly my drone, but nowadays every drone has an embedded GPS, and produce the output of that. Can be a point cloud, can be an orthomosaic, already in your local coordinates. And you can directly include that point cloud, that orthomosaic, into your project. That's already in your local coordinates. Okay, so here we are going to see an example of how things done and how we match points. So in a local coordinate reference system, you need some reference points in your field. So probably a surveyor went there and marked some points. In the example, there are 4, S1, S2, S3, S4, and with known coordinates. As you see, S1 has 500, 500. Usually they don't start with 0 to avoid negative numbers. So the reference, the 0, 0 is a bit far away. And with a total station, if you want to find out the position of the 5th point there in the center, you measure the angles, and you can deduce the location of this point. We know the coordinates of these 4 points in this local reference system. What we are going to do is to measure the location of those points with a GNSS receiver. In the example here, I just select one random geographic coordinate reference system, ETS89, and we measure the points in latitude, longitude example. By the way, all those the numbers are fictional. Don't try to find any actual connection between them. So we have side points in measuring meters or in feet, any linear distance. Remember that the local CRS is a Cartesian coordinate system. We have the global points that we did measure in a latitude, longitude in a geographic system. We have the definition of this global CRS, and what's missing is the definition of our site CRS. That's what we want to find. When we have it, we can do transformations between these two, actually to any other CRS. And we want to define this CRS in a way that we can do that transformation. So how are we going to define site-calibrated CRS? First, we'll need a base-projected CRS centered in the area of interest, because we want to minimize local distortion, the projection distortion, and also the high distortion. In top of that, we are going to apply a translation, a rotation, and a scale. That sounds a fine transformation, we'll see later, that can be expressed with 7 parameters. These 7 parameters are not the same as in a Helmert transformation. Remember that Helmert transformation is applied at the center of the Earth. You go to Cartesian, but at the center of the Earth, and then you apply that there. This is happening in the projected CRS. So this transformation is happening at the surface of the Earth, not on the center. And we need a projected CRS. So we will choose a CRS centered in the area of interest. UTM is not centered in the area of interest, so it has distortion that can be significant in some cases. And it's a good idea to use a conformal CRS, so that keeps angles, because probably we're using that for surveying, and we want to minimize distortion that way, but it's not mandatory. So I've seen private realizations that looking at digging into the documentation, you find out I was using another one, I think was orthographic, I'm not sure, but it was not conformal. Okay, so on top of that projected CRS, we're going to apply a rotation, scale, and translation. This formula there is, I try to use the same letters as in the paper. The rotation, it's a matrix. Can be a 2D or 3D rotation. T is a translation, a vector, and C a scale. And that transformations fits very well with what PROJ has as a affine transformation. This is the formula in the PROJ documentation. Actually, PROJ has the 4th dimension, that's the time, but we don't care here about time. So we can encapsulate scale and rotation in this matrix, S1 and so on. The translation is X off, Y off, Z off, and that's all. But we have to compute these 3 parameters, the scale, the rotation, and the translation. For that, what we are going to do is to compute the residuals and trying to minimize them. Residuals is the difference between the local coordinate that we measure, the green values on the table a few slides before, and the transformation with these parameters from a well-known coordinates, or from what you measure from your GNSS receiver. So these two things are linear in meters or feet, and the difference is how much is your deviation from your point. We want to make it minimal, and that's the equation we want to solve. Minimize the residual, the sum of all them squared. There's a well-known algorithm published last century. There's Umeyama that minimized that. It's demonstrated that this solution is the minimal. It works on any dimension. We are going to use 2 or 3, but if you're interested, this works on any dimension. And we are using C++ Eigen library, that's open source as well, to solve this with this function Eigen : Umeyama. But we realized that we started solving that on 3D, and you can see here that the rotation matrix, actually here, is a 3D rotation matrix. But we realized that the noise on the vertical component, because GNSS receivers has a worse accuracy on the C direction, can introduce some noise on the horizontal measurements, because we are making a 3D rotation. So we try, and it works very well, splitting in horizontal and vertical calibration. And in these graphs here on the left-hand side, you can see that's a 3D calibration, so the rotation is 3D. So any noise on the vertical component, that's the x-axis, introduces some noise on the x, y, and the horizontal RMS, as you can see there. But when we split in two, because there are two different calibrations, it's not affecting it. And that also helps the user to select different points to calibrate the horizontal part and the vertical part. Sometimes they have much more points measured in 2D, x, y, and they have just one or a few points on with a C value that's really reliable. With that, you can use more points on the horizontal, well, different number of points. So for the vertical calibration, what we are using is this function in EPSG that was that's implemented now in PROJ, vertical offset and slope. That's the formula there. It sounds a bit complicated, but it's much simpler. The only unknowns we have are the letters in capitals. Set of the I, phi, and I lambda that are the offset of a point, and the slopes on the latitude and longitude direction. So it's a linear system. We can solve it with a least squares method, and yeah, we need for that at least 3 points with a vertical coordinate. Okay, so what is WKT2? Because that was on the title of the presentation. It is a well-known representation of a coordinate reference system. There was a version 1, but it was not fitting the needs we have here. So to add this affine transformation and the vertical offset and slope I was telling before was not doable. I didn't find at least a way to do it with WKT1. But with WKT2, there's a way to do that that helps a lot. And will allow us to define the local coordinate reference system already calibrated, self-contained. So it will be just one file, one string that defines completely the CRS. So we can use it to define it and to transform just to any other system in just one thing. We don't have to split. Here is the projector, here are the parameters. No, it's all together. Let me show you here an example of a WKT2. Can be very verbose, so please don't pay so much attention to the gray text. Just look only at the color words there. So first thing we have is a compound CRS. This example is splitting horizontal and vertical, and for that we need a compound CRS to define first the horizontal part and then the vertical. And the first entry is this derived projected CRS. That's the horizontal part. That has first base projected CRS. That's this projected first coordinate system I was talking before. In this case, it's a transfer Mercator. You can use any other Lamberkoff-Marconic or any other projection you like. That is centered on the area of interest. So it's really interesting that the origin of this projection is where we want to work, in the construction site, on your backyard, or wherever you are going to define those points. And on top of that, that's because it's a derived projected, we have a deriving conversion. And this is the parameters I saw you before about this offset and rotation and scale embedded in this matrix. In this case, with this PROJ-based operation method. There are other options in WKT2 that are included now in EPSC, but you have less control over the axis order and units. So me personally now I'm more comfortable with this because everything is under control. And the second component of this compound CRS is a vertical CRS. This is a definition of a derived vertical CRS with base one. In this case, I was using ellipsoid. It's a bit of a hack. It should be a proper vertical system, but the measurements were not done on that vertical system, so I was using that. And a deriving conversion. This deriving conversion is this vertical offset and slope I mentioned before. It should be centered somewhere, can be the same point as before, doesn't have to, and has a vertical offset and these two inclinations or slopes in the latitude and longitude direction. And that's all. We have the CRS defined. And let me talk a bit about PROJ. So, well, it's a C++ API. We use directly on C++, not in the Python. And we use that to create the coordinate reference system, the initial ones. Obviously, this projected transfer Mercator, that's the projection we were using, to create all the deriving conversion and so on, and obviously to create the WKT2. So the output of our function was, the input was the input points, the side points, and the points measured with the GNSS receiver. And the output was the definition of, the input was also the coordinate reference system of the GNSS receiver, and the output was the definition of the CRS. And of course, we were using PROJ to do any transformation, to check the residuals and so on. And I would like to thank Eigen that's here, Eigen, that he helped us a lot during the development. We found some bugs or missing functionalities that, he answered pretty quickly, or PRs and mails. And just as a summary, the main ideas is that we are using WKT2 to define a CRS that encapsulates the site calibration. It's self-contained, it's plain text. You can read it, you can understand it, it's open source. And this compound CRS, the structure of this WKT2. That's all. Thank you.